Welcome to Chapter 17, Part 2. Geometric distribution we talked about the other day. Well, it was really in a worksheet. I'd kind of typed out all of the notes there. Just to review what that was we talked about the geometric distribution in terms of we have the question. There was a setting, a geometric setting, if you remember in that problem in that worksheet. It said the following three things. You had to have success or failures. I have to be able to characterize my outcomes and success or failures. I have to be able to say the probability of success is constant and that the trials are independent of each other. If those three things happen, then you have what we consider a geometric distribution. The other part was the value, what we assigned to x. And in this case, we said that x is the number of trials to find my first success. The only other side, we have the binomial distribution. A few things that kind of are consistent. We call P the probability of success, Q, which is 1 minus P, this is the probability of failure, and N is my sample size. Now, I don't always see N on this side because we don't have a specific number of trials, but in this case, N is the sample size, or in this case, it'll be trial size. When we're looking at the binomial distribution, each of these have their own formula for mean and for standard deviation, accordingly. We also have a setting for the binomial distribution. The one additional element that we have for binomial that we don't have for geometric, and I want to make sure that we know that 1, 2, and 3 are also true for the binomial. It has to have success or failure, and the probability of success has to be constant, and the number of trials, or the trials, have to be independent of each other. But binomial has an additional one. It has a fourth element. It has to have a limited trial size. In other words, I have to say there's 20 trials, there's 15 people, there are whatever specific number of trials. X in this case is asking for you to determine the number of successes out of n trials. So if we're going to flip a coin, then a binomial setting would be something like this. What is the probability that I could get 5 heads out of 10 flips of a coin? Whenever you're given the number of trials and you're asking to find a specific number of successes, this is what you would consider a binomial setting. For example, we have one here, type O blood example from your book. In this example, it asks us a few questions. Number one, it says that the probability of having type O blood is 6%. And in this scenario, you had 20 people walk into a blood donor, a clinic, and they were going to donate blood. The question would be, for a binomial setting, would be, first of all, you could ask a question like this. What is the expected number of people out of 20 you would expect to have type O negative blood? Well, anytime you use the word expect, you are describing a mean of some type, an expected value. In this case, we would do N times P. This would be equal to 20 times 0.06. This would be equal to 1.2. So anytime you had 20 people walk into a room, the probability of success is 6%. We would expect about 1.2 people, and definitely leave it as a decimal. This is always an estimated value. 1.2 people to be O negative blood type. Another question we could ask is, what's the probability that you could have 2 or 3 people out of your 20 have type O negative blood? Well, we're back into what we would say binomial Pdf or binomial Cdf. If you remember from the geometric distribution, if you've read your chapter, you know there's two possibilities. You have specific values, like exactly one number, the probability of having 2 people with O negative blood, or it could be a cumulative value. I could have, let's say, up to 3 people with O negative blood. I'm referring to this point more than one value. Now, specifically, the binomial or geometric CDF, the cumulative distribution function, essentially adds up all the values that you would do. It would be like a PDF of 2, a PDF of 3, a PDF of 4, a PDF of 5, and you would simply add them together. That would be what you consider PDF or a CDF. In this case, we are going to take this one, since it's only 2 values, I really can use it in both ways, PDF or a CDF. I think for me, I would probably do this one as a PDF. And so if you don't know how to find this in your calculator, it's second vars, and then you're going to press up. Okay, it's going to take you to the bottom of that list, is where you'll find geometric first, and scroll up a little bit more, you're going to find your binomial PDF and CDF. We're going to use binomial PDF here because I'm using it for a specific value. I'm going to say n, my trial size is 20. The next part is going to be the probability of success, so that's 0.06. The third probability, or sorry, the third number is how many successes you want it to find. So this binomial PDF of 20.06 and 2 will tell me the probability that 2 people walk into that clinic having type O blood out of 20. We're going to add that to the binomial PDF of 20.06 and 3. When I add those things together, this is going to give me the probability of doing one or the other, because or indicates an addition problem. You have 2 different things, and you can work it out that way. And I would probably type it in just like you see it on my calculator. Binomial PDF of 20.062 plus the binomial PDF of the other thing. Let me erase this because that looks like plus or minus, and that is not what we're doing. It is just plus. Right, work this out, you get 0.3106 as your result. So there's a 31, just slightly more than 31% chance of you getting 2 or 3 people to walk into the clinic that have type O negative blood. The other 2 elements in this chapter that I think are really important to go over is 10% condition and the success or failure condition. These 2 things are going to kind of show up in this chapter, and they're going to come back pretty much every chapter from this point on. The question is, when I use the 10% condition, it's really justifying independence. We know that one of our conditions at each trial has to be independent, right? But technically speaking, if we have a sample size from a limited population, if I'm choosing a sample of, let's say, 1,500 people, every time, if we knew that 6% of the population were out of this group was type O negative blood, well, the moment I put 1,500 names into a hat and draw out a name, the probability of me choosing another person with type O negative blood, well, it's no longer 6% because now I have 1,499 names out of what I originally had 1,500. So really, by choosing without replacement, which unless we are dealing with an infinite population like rolling dice, I can always roll the die forever, I can flip a coin forever, but I can't choose names out of a hat forever. So by definition, we are essentially choosing without replacement, which means this is not independent. So we need to kind of go over that. We're going to basically fudge the numbers a little bit. We're going to say, okay, we understand that that's not really independent, but it doesn't change the probability that much to start with. Eventually it will change too much, and I'm going to have to draw the line. And we draw that line at 10% of the population. And so the way we can check that, if I take a sample, let's use our school as our population. If I did 0.1 times 1,500, that would equal 150 people. I can take a sample of 150 or less, and we can consider that independent, even though we are sampling without replacement. Most of the time, I don't really know the population, so it usually works backwards, right? Sometimes I'm going to tell you have a sample size of 300. That sample size of 300 has to have a population of greater than or equal to 3,000 people, right? And as long as my population is larger than that, then I'm okay. I am satisfying the condition for 10%. If it breaks that rule, if my population in this case was only 2,000, and I took a sample of 300, then the independence condition here doesn't hold true. And so I have to be able to go backwards and say that doesn't work. Okay? That would fail, and it would not be binomial. It wouldn't be Bernoulli trials, which is binomial and geometric. Okay? Switch gears. success or failure condition. This is an entirely different condition. It's asking, well, can I use normal CDF to estimate binomial? This only goes with for binomial distributions, right? It does not count. It doesn't even, you don't even make it into the conversation about geometric. It doesn't happen, right? And the deal is that if n times p is greater than or equal to 10, and n times q, if that's greater than or equal to 10, then yes, you can use the normal model. I can use that whole concept of, I can have a mean, I can have a lower bound, I can have an upper bound, and I can find the area in between them, and I can get that percentage, and that would essentially become my, and of course you need your standard deviation for this, I would have to be able to say that. And what really happens is I have to justify it by doing that calculation. How many expected successes am I going to have? N times p, that's actually your mean. And how many expected failures? Either way, the sample size needs to be large enough to make it turn into a normal distribution. And we're going to draw that line where you have to have at least 10 of each expected successes and expected failures. Okay, that's all there is to this. I recommend you read the chapter about these two things. It'll add a lot more clarity to this. If you have any questions, let me know.